All right, so let's talk a little bit about what we did on Monday.
Oh,
Monday was mostly review, but we kind of added something. So
all right.
if we think about reactions that have to do with, oops, reactions that have to do with alkyl halide. So an alkyl halide is just any sort of halogen on a carbon containing group, right?
Yeah. hmm
So this tends to be what?
Uh,
Nucleophile,
tends,
electrophile.
tends to be a nucleophile.
Oh, test
Oh,
failed.
electrophile. My God,
Right. This
not a
is why
fan.
we draw this chart at the beginning of every class, right?
Yeah.
So the thing with it is that there's really two electrophilic places. Either it can, wow, that's a really big circle, but either something can add into this carbon, right? So either we can get some sort of addition here,
Yeah.
or what can also happen is we have a kind of acidic proton here.
hmm
So if I have something with excess electrons, it can either take this proton or it can
Yeah.
attack this carbon.
Yeah.
So if I take this proton, I'm going to get what's called an elimination. So
hmm
let's kind of draw these two situations out. So if I take this proton, I'm going to leave the electrons behind.
Yeah.
And I'm going to kick off that bromine to make room for these extra electrons. And I'm going to end up getting this.
Yeah. I recall.
Transversely, if I have some kind of nucleophile add into this carbon, what you see is it replaces the bromine or the alkyl halide, whatever that halogen is.
hmm
And what kind of reaction is this? What have I done?
Replaces it. This is a substitution.
Right. So I have, whenever I have an alkyl halide as my electrophile, I can either get elimination or I can get substitution.
Yeah.
Cool.
hmm
So what we did last week was talk about situations where we would get elimination or substitution, and even there's different forms of elimination and different forms of substitution. Right? Either this happens in a one-step process or it happens over two steps. Right? Either the
hmm
alkyl halide leaves first, and then I um, do the second part, or it all happens at once.
Okay. Is
Um,
it
so that was last
fastest?
week.
Okay. Is it fastest on SN2 E2s and then
Yes.
like two steps and SN1, SN1? Okay. Okay.
And really what I'm looking for is anything that's charged tends to be the slower. So that's going to
Okay.
be your SN1 E1. So that's charged nucleophiles. So
Okay.
or sorry, I said that backwards. Uncharged. That's going to be slower. Right? Charged things are more reactive, right? So the textbook comparison would be like if I have something like this, right? That's uncharged, right? There's no charge on this. But if I have something charged, well, now the reaction speeds up. It all happens in one step. So now I get SN2 E2. And so the kind of analog for this would be this charged. Right. This is more willing to give up its electrons. This reacts faster, right?
Mm,
Another way you might see this is this. It's another common way to show a charged molecule. Right.
yeah.
It's an ionic bond between the oxygen and the sodium, right? So these are the fast ones. These are the ones that happen like I'm showing here in one step, the SN2E2. Um, the uncharged happen in two steps. So instead of something like this, you would see, oops, you would see something like this, where that doesn't happen yet. We get the first step with the bromine leaving, forming a carbocation,
Yeah.
and then the nucleophile attacks.
Yeah, I got you.
So that was last week. We kind of talked more situations about how to determine SN2 versus E2 and SN1 versus SE1, but today I'm going to try to catch you up on what we did on Monday.
Okay.
So Monday we kind of went into the specifics. So if you noticed in elimination, I could have taken from a hydrogen to the right side of this bromine or a hydrogen to the left. So how do I decide which one? In this case, it doesn't matter because I would get the same molecule either way, right? They're equivalent. But let's do a situation where it's not equivalent. So let's add a carbon here. So I can either take this hydrogen or I can take this hydrogen, right?
Yeah.
So which do you take?
I think you should take the right one
Why should I take the right one?
because it's more stable.
So if I take the right one, this is the product I form, right?
Mm.
If I take the left one, this is the product I form,
Yeah.
right? So what makes you say that this one is more stable?
It's on a secondary. Yeah, it's on a secondary carbon.
What is on a secondary carbon?
Well, the hydrogen.
Okay, yeah, this hydrogen's on a secondary carbon.
Yeah.
So that creates a double bond here.
Yeah.
We call this a disubstituted a double bond. So on the double bond, on either side, there's one, two things coming off of it.
Mm.
Whereas this double bond, there's only one thing coming off of it.
Mhm.
Right? So this is a monosubstituted double bond. So this disubstituted double bond is a more stable double bond. So typically in these reactions, if I give you the choice, I want you to be able to tell me, hey, this is the elimination I'm going to receive.
Mm.
Hey, Natalie.
Hey,
So
I just need help with everything.
yeah, we're catching Michael up on what we were doing on Monday.
Okay.
So this is you guys are actually in opposite places where Michael caught everything last week and you and missed Monday and you caught Monday and missed everything last week. Right. So right now I'm just talking about eliminations and how we're going to form the more stable, the more substituted double bond, right? The one with the most things coming off of it, right? This being a disubstituted, right? I've got one, two things coming off the double bond, where this double bond only has one thing coming off of it.
Yeah.
The other thing we talked about is if you get, I'm going to see if I can draw this. SN2 happens over one in one step, right? It's a concerted process is what they call. So let's draw this. So if I have some sort of alkyl halide, let's use just chlorine here. And I've got some kind of nucleophile. Doesn't really matter. So I'll just steal this guy. And I'm going to do an SN2. So what tends to happen is, well, not what tends to happen. What does happen is this is a one-step process. Oh. Okay, sorry. I just hit a bunch of backspaces. So this is a one-step process, right? So this guy's going to attack into this chlorine,
Mhm.
and the chlorine's going to leave all in one step. Sorry, it takes a second to draw this stuff.
Yeah.
So what we call this is we call this a backside attack, right? So when this attacks, when this does this substitution, it's not approaching the same face that the chlorine was on because the chlorine was on this face, right? The chlorine was on the right side. So you actually get an inversion. where now notice this oxygen's now on the left side where the chlorine was on the right side.
Mhm.
Right. So this is called an inversion of stereochemistry. The upshot of this is if I were to give you this same reaction and it looked like this, well, when I do the displacement, you're going to flip the stereochemistry of the substitution. So
Yeah.
when this gets substituted, it doesn't show up like a wedge like the starting chlorine was, but now it's a dash.
Okay, I got it.
Right. So this only happens with SN2s, but you need to be aware with SN2s.
Mhm.
This doesn't happen with SN1s. With SN1s, what happens is, let's say this was an SN1. So how could I do the same reaction but make it SN1?
So you would draw out the bond from the chlorine.
Okay.
Uh,
How
oh,
could I change this to encourage an SN1
okay,
substitution?
sorry. No, put a hydrogen on it.
Okay, let's put a hydrogen. Let's make it neutral, right?
Mhm.
So now I'm looking more at an SN1 type mechanism, right? I've slowed things down. With this SN1, this leaves first. And what I do is I form a carbocation. Oops. Hey, little man. Can you hear him?
No.
No.
Okay. He's a little upset, so I'm gonna go tend to him in a second. But
All right, cool.
all right, so when you get this, when you get the carbocation, this nucleophile, unlike this one where it can only approach from the opposite side of the chlorine because the chlorine's sitting here, it can approach from either direction here. So it can come this way, or it can come this way. Oh, it's the oxygen, sorry. Little man is sick. So either I can get attack from one direction or I can get attack from the other direction. That means that when I get the substitution, I get both this product and this product. So SN2 is selective, and you get an inversion of stereochemistry. SN1 is not selective.
So which arrow from when the oxygen is attacking the carbocat, which one's front, which one's back?
I mean, it doesn't matter. It's just that there's no front or back. It can add from either direction.
So you're saying that if we just
Like
draw
the arrows don't show front or back. I'm just trying to show that it can approach from two different directions.
so either of those products would be fine if we
Technically, you're going to get both.
Okay.
Right. So
Okay.
you can
I see.
this is called a racemic mixture. Two different. So you can either draw both, or one thing that I didn't talk about in class, but is also okay. If you drew it just without stereochemistry and just told me it was racemic, which is that word, that would work as well, right? So both of these things say the same thing, that I get both products with an SN1. Right. So this is kind of the selectivity of SN1, E1, E2, SN2, E2. With eliminations, we tend to form a more substituted alkene. With substitutions, SN2, you get a flip of stereochemistry. SN1, you get both.
Hmm.
One more thing I want to talk about, or that I did talk about, is this step. With both SN1 and E1s, here, wait, let me pause this. I will come back in a second. All right, one more thing I want to talk about is this step here. With SN1s and E1s, you form a carbocation. So let me draw, let's do another just example carbocation. Anytime you form a carbocation, you need to have your eyes open for what?
Good. Which carbon it's on?
Okay, what kind of carbon is this carbocation on?
Secondary.
It's on a secondary. What do we want to do with our carbocations?
Move it so it's on a tertiary one. So this would do a hydride shift.
Right. The more substitute the carbocation, this is secondary,
Mhm.
right? Because there's two other things attached to it. If it was over here, it'd be primary. We want to get it onto the most substituted carbon. So we have two tools to do it. We can either do a hydride shift or a methyl shift. We prefer to do hydride shifts. So
Mhm.
essentially all that means is there's a hydrogen here. And if we can essentially trade places with this hydrogen, with this bond, with this carbocation. And what that essentially does for us is, where does it put the carbocation?
On the tertiary.
It puts the carbocation on a tertiary. So we see this in both E1, E2, or sorry, E1, SM1, and we see it with the addition reactions, right? Last time we saw this, it was when we had reactions that look like this, where we would add some kind of acid. Right. When we did these reactions, we would also form carbocations, right?
Mm.
So you have to be aware anytime, and this goes for any reactions in this class. Anytime we form a carbocation, oh, I want to do this. Anytime we form a carbocation, you have to be aware of carbocation rearrangements. Right. So this happens in this reaction, it happens in this reaction, right? And these are both reactions that could be on the test. So that's going to be a big part of the test. So like if I had a similar situation where I did an addition reaction, I had this, I would see this hydride shift. Or if I had this, when I form this carbocation, I would see a hydride shift and form different products because of it, right? So anytime you form a carbocation, look for hydride shifts, look for methyl shifts. So that is the new stuff. That is the stuff we went over Monday. It's kind of the more granular parts. It's kind of like if last week you understood everything, you're gonna get a 90 on the test. This will get you 100, right? These are like the specifics. These are the like, all right, you're understanding substitution, you're understanding elimination. Now understand the more specific parts about it. Where am I going to eliminate? What's the stereochemistry of my substitution? Is there going to be a carbocation rearrangement? Does that make sense?
Yeah, that makes sense. That's good.
Okay. So I would say that I've given some practice problems out both last Friday and on Monday. And tomorrow we're going to do something slightly different. But I would make sure that you practice those things. I would make sure that you can differentiate between SN1, E1, SN2, E2.
Okay.
So
sounds good. Cool.
So just for a little bit of practice, right? Just to talk about this a little bit more, right? So charged, uncharged. This is actually the second thing you want to look at. The first thing you want to look at is what kind of alkyl halide do you have? So if you have primary, it's going to be SN2. End of story. Secondary, and I'm going to draw them for you in a second. It can be any of them. So secondary is tricky. That's why I kind of teach it last. And then tertiary is any but SN2. So you don't get any SN2, but you can get E1, E2. So what I mean by primary, secondary, tertiary is if X is a halogen, like a chlorine, bromine, so a primary alkyl halide is this. A secondary alkyl halide means that there's two things on this carbon. A tertiary alkyl halide means that there's three other things attached to this carbon, right? So, let's see if I can pull up my practice. So, let's go through it. I'm going to just redraw the practice problems. And let's think about how we want to approach these questions. All right. Oh, I'm missing something. Question 1. What's my nucleophile?
What's the
Do I have a nucleophile in this picture?
it's your OH.
Probably my alcohol, right? Do I have an electrophile in this picture?
It's your bromine.
It's my bromine. It's the carbon attached to this bromine. So I've decided, because it's an alkyl halide, now I'm in my SN1, SN2 phase, right? What kind of alkyl halide is this?
Tertiary.
Right. This is a tertiary alkyl halide. So I know it can't be SN2 right off the bat. So I'm talking E1, E2, SN1, right? This guy, is he charged or uncharged? That's my nucleophile, right? So this is my
Uncharged.
electrophile, this is my nucleophile. What?
Uncharged.
He's uncharged. So now I can eliminate something else, right? It's not going to be E2. So now I'm thinking it's SN1 or E1. Final thing is heat. And I didn't talk about this earlier, but heat favors elimination. So what kind of reaction does this have to be?
It's E1.
It has to be E1, right? It can't be E2 because it's not charged. It can't be SN2 because it's tertiary. So it has to be E1. So the mechanism of E1 is this bromine leaves first. And then I have a question. I have to do elimination. Where am I going to eliminate from? I can either take a hydrogen off this carbon, a hydrogen off this carbon, or a hydrogen off this carbon. Which one am I going to take?
The last carbon.
Why?
Because it's secondary, it's the most stable.
It's going to form the most stable alkene. It's going to form the most stable double bond, right? If that would just be a di substitute double bond, same with this. So I'm going to take this one and we're going to form this. Now I'm going to have to hop off here in a second because Arlo is not happy. So this is how I'd approach this reaction. Obviously, I would want to do the mechanism here to get the product, but yeah, that's my thought process. Go step by step, find the nucleophile, find the electrophile. And the thing is, on this test, we haven't only gone over SN1, SN2, E1, E2. So be careful, right? Sometimes these distinctions don't apply, right? I purposely threw in this question and the next one to make sure that you guys weren't going full robot mode. This is the next question. What's my nucleophile? Do I have a nucleophile?
Doesn't look like one.
Do you have the chart that has nucleophiles and electrophiles on it?
I gotta find it.
Natalie, can you help them out? All right, so do I have a nucleophile in this picture? Based off the chart that we've gone over in class.
HCO.
Do I have a
No, but this
nucleophile?
is the double bond.
The double bond. This is the closest thing to a nucleophile I have in this whole picture, right? I don't have an alcohol or an amine or anything negatively charged. What is HCl?
An acid.
An acid. What do acids do?
They donate hydrogens.
They donate hydrogens, right? They donate protons. What do I need to take a proton?
Where do you need to take a proton?
Right. I need to take a proton, right? Protons are these positively charged things. What do I need to have to
A
go?
negatively charged thing.
I need something that's negatively charged. I need electrons, right? To grab a proton, right? Right, that makes sense. So
Mhm.
do I have anything that's got electrons in it?
It's the double bond.
I've got a double bond, right? So we're not going to be in robot mode. We're going to see that this is an acid. So we're going to protonate something. The only thing with electrons that can take the proton is this double bond. Arlo's grabbing the microphone. So we're going to leave the chlorine behind and we're just going to take the proton. Oops. It's a little bit harder with a baby in your lap. So I'm going to put the proton on one of these two. What happens to the other one?
It goes positive.
It just lost a bond, right? This double bond was shared between this carbon and this carbon. Well, now this carbon made a new bond, which means this guy's lacking a bond. I've got a carbocation. That means I'm looking for what?
Shifts.
I'm looking for any shifts. I'm looking for any rearrangements. Is there any shifts I could do that would make this secondary carbocation better?
Mm,
No.
No, right? Because it's just surrounded by other secondary carbons. So now I've got a negatively charged chlorine sitting around. It's going to add into this positive, and we're going to get this. Right, so we're not going to be in robot mode. Not everything's SN1, SN2, E1, E2. Right, not everything. That is only when I have an alkyl halide as my electrophile. This is an addition reaction. Right, so we got to keep our eyes open. On the test, it's all fair game. All right. We'll just do a couple more. And this was the next one on the practice, so. Yes. All right, so let's talk about this reaction. Do I have a nucleophile here? Do I have something that wants to give away electrons?
NaS and nothing.
Right, so a sulfur, you can think of as like a big oxygen, right? So if I had written this, right? These are saying very similar things, right? A negatively charged oxygen. Now I've got a negatively charged sulfur, right? So this is screaming, hey, this is the thing that's probably going to give electrons. It's a charged sulfur, right? It's a negatively charged sulfur. We know that because of the sodium, right? Anytime you see anything with a metal, that's where your eyes should go first. Cool.
Mhm.
Do I have an electrophile?
The iodine.
Right, this alkyl halide right here, right? So since my electrophile is an alkyl halide, I'm asking a few questions. First question, what kind of alkyl halide is it?
Secondary.
It's secondary, which means that I have any possibility. What is my nucleophile like? Is it charged or uncharged?
Uncharged.
It's uncharged. No, that's not true.
Charge,
Oh,
that's
it's charged.
negative.
Oh, I know, right?
Right.
It's the middle.
There's the sodium on it, right?
Right.
So it fits in this charge category. So since it's secondary, it could be any, and now I know it could be SN2 or E2, right? So I'm stoked if you can get to this level. If you get here and then you're like, well, I'm not sure if it's elimination or substitution, we've gotten to a good point. You're going to get some partial credit on this. The last thing is the difference. One of the differences between substitution and elimination comes with how delocalized that negative charge is. So if I compare a sulfur to an oxygen, the negative charge on the oxygen is less spread out than the negative charge on the sulfur. The more spread out a charge is, the more likely it is to be substitution. So really the only way you'll see that is with like sulfur. Or what I call carboxylates. So any sort of sulfur nucleophile or like a negatively charged something like this, where the charge is spread through resonance. These two things kind of they favor substitution. So if I'm favoring substitution, what kind of reaction is this based off everything else?
SN2.
It's got to be SN2 because this is charged, right? So substitution, it's going to happen one step because this is charged. So I'm going to get substitution. And what do we know about the stereochemistry of SN2?
It's the opposite, or like an inversion.
Yeah.
You get an inversion, right? So not only am I going to get this substitution, but I'm also going to get an inversion of the stereochemistry. Does that make sense?
Mhm.
All right. So we'll keep on trucking. So this was the next one on the reaction list on the practice problems. All right, so the first thing I want to do always is decide what the different components of this reaction are. Do I have anything that screams nucleophile? Look at the chart.
The OH.
Yeah, is it?
The alcohol screams nucleophile, right? Yeah?
Yes.
Do I have anything that screams electrophile?
The
Double bond and oxygen.
Yeah, sorry, Arlo keeps taking my headphones out. Yeah, this carbonyl. Right? So I've got a nucleophile, I've got an electrophile. I'm not in robot mode. Is my electrophile an alkyl halide?
No.
No, then I'm not worried about SN1, SN2, E1, E2. That's only alkyl halides. Oh, poor dude. So now I just follow the rules of a reaction. I've got an acid, I've got a nucleophile, I've got an electrophile. What am I going to do?
This
Are you going to move electrons on the double bond?
Okay, what do acids do?
Donate hydrogens.
They donate hydrogens. Where is it going to donate its hydrogens to?
the electrophile.
To something with electrons, right?
Would it be the double bond and oxygen?
the question is, right, I've got lone pairs on this oxygen and I've got lone pairs on this oxygen. So which one is it going to go to?
The
Do I-
double bond.
Do I want to protonate my nucleophile or my electrophile?
Electrophile,
Why?
Mhm.
because it wants hydrogens.
Why?
I don't know.
It can handle them, like
What is an electrophile?
electron loving.
It's electron loving. How do I make something even more electrophilic?
Make it
What's the most electrophilic thing you can think of? What's something that screams, I want electrons?
you have it there. The
What's something that
Yeah.
has a sign on its head that
A
says
positive.
a positive charge, right? Something that's more positive is more electrophilic. So if I'm trying to make my electrophiles better and my nucleophiles better, where might I put a proton?
Where
on
there's
the
a
FO.
What? Protons make things more positive or more negative?
more positive.
More positive. Yes. If I want to make my electrophile better or I want to make my nucleophile better, what do I want to make more positive?
The electrophile,
Why?
because it's already more negative, so it can. I don't know why, but I know we've done it before.
You can have a
Electro-
stronger reaction between nucleophiles and electrophiles when they're more positive and more negative.
Right. If I can make my electrophile even more positive, right, it's going to want electrons even more. If I'm going to make my electrophile negative, it's going to want to give away its electrons more, right?
Yes.
Yeah.
Yes. So if I have an acid, I'm going to protonate my electrophile. This is something we did a couple weeks ago, but it's going to be on the test.
Oopsie.
So now I've got this. I've protonated my electrophile. Right. Now this thing is supercharged to be a good electrophile. Yeah?
Yeah.
Do I have a good nucleophile? Do I have a nucleophile around?
Yes.
Yes.
Yes. So the nucleophile attacks the electrophile. Thing. Nucleophile attacks the electrophile. Always into this carbon, never into this oxygen. I know the oxygen's got the positive charge, but we want to push the electrons up into the oxygen. So then we form our final product. Nope. Oops. Does that track? Are we following?
Yes.
Yeah.
Sorry, I'm having to do this one-handed. Where this ethanol ended up being here, and it should still be charged, right? As a proton on it.
Hmm.
Right. So this is kind of a broad scope. I don't want you guys to get into robot mode. I want you to say, what's my nucleophile in the picture? What's my electrophile in the picture? If it's an alkyl halide, well, now we've got to be watching for eliminations and substitutions. If there's not an alkyl halide, we follow our normal rules, right? If it's an acid, give it to the electrophile. In this case, I had no electrophile, so I had to give it to the nucleophile. Right? I had to give it to the only thing that had electrons. Sweet dude. Um, is that tracking?
Yeah.
Okay, so I want you guys to go back and practice this. I might hold another office hours because I'm cutting this one a little bit short, but Arlo's getting a little fussy. I'm gonna post this online, this video online, and I might have some more office hours tomorrow. I'll announce it in class if I do. So, but I'm gonna head off. I think he's about to get kind of mad at me. So, thanks
Thank
for
you.
showing up. Is there any specific
you.
questions I can answer without kind of drawing real quick
I
that
have
you
a
guys have?
quick question just
Yeah.
about the test content. So you mentioned that it's going to be cumulative. How much should we focus on like previous stuff?
If I'm being honest with you, what I want you to focus on is the kinds of questions that I put for practice. I want you to be
Okay.
able to do SM1, SN2, E1, E2 with the mechanisms. I want you to be able to do the addition reactions, which is the double bond reacting with an acid or with something else. And I want you to be able to, in general, like that last question, I might give you something that's not one of those two, like an addition into a carbonyl. So I want you to be able to say, I want you to be able to identify in every reaction, hey, this is the nucleophile, this is the electrophile. Do I have an acid or a base? And then I can follow the steps.
Okay.
I can
Perfect.
intuitively follow the steps. I'm going to be straightforward. Do not spend your time studying Newman projections or chair structures. Those will not be on the test. I want you to be able to do reactions. I want you to be able to sit there and for every one of these reactions, label the components. And I know that if I have an acid with a nucleophile and electrophile, I'm going to protonate the electrophile and I'm going to go from there. If I have an alkyl halide as my electrophile, I'm going to have to determine SN1, SN2, E1, E2. If I have an acid and I don't have an electrophile, well, the only place I can put it is on the nucleophile, right? Like
Mhm.
follow the electrons. I want you, like an example question would be like what I gave you on Monday. And I would then say, give some partial credit for, hey, can you label the components correctly? Can you draw the correct mechanism? Can you do something that's reasonable chemically, right?
Mhm.
Even if you don't get the right answer, can I see where you're going? Like if you miss a hydride shift, but you get everything else, well, you're probably going to get 4 out of 5 points or something like that.
Okay.
So it's going to be a bunch of that. It's going to be a bunch of, I want to see that you've got the process down to being able to see these reactions. And that's kind of what I'm doing. I would not go back too far. It's going to be everything since the last test, essentially. And of course, I'm going to throw in some mechanism questions where I'll give you starting materials and final product, and you have to fill in the arrows, or vice versa. That's going to be fair game for the rest of the course. I'm always going to ask those questions.
Okay.
He's just out of frame. Say hi.
Aww.
He's a dude. He's not feeling well today. Any other questions? Did that answer the question?
Yes. Thank you so much. I appreciate it.
Yeah.
Are addition reactions like the same thing as like whenever we had that like nucleophiles and electrophiles and like made them to like how those react?
What do you mean?
Like the last one we did, is that an addition reaction?
Uh, it is, but yeah, the names aren't really that important more than it helps just talk about them. But yes, that last reaction we did where we added the ethanol into the carbonyl, that is also an addition reaction because you're just adding something, right? You're not taking anything away. But it is kind of confusing because the double bond stuff is also addition reactions. Those are more formally addition reactions.
Okay.
We would call that an addition into a carbonyl, really. But it's less that like I want you to memorize these reactions and more that like I want I want you to be able to fight for partial credit. I want you to be able to say, this is the nucleophile, this is the electrophile. I know that nucleophile is going to attack electrophile. And maybe I've got an acid in there. Maybe I've got a base in there. What do I do with that? Right? Because acids do a certain thing, right? Acids give away protons, bases take protons. So I can understand when I would use an acid and what I would use an acid for. I can understand what a typical nucleophile looks like, what a typical electrophile looks like, and I can follow those steps. That's my goal for you. That's what I'm trying to teach you to do, more so than be in robot mode and be like, well, this is SN1 because blah, blah, blah. Like, yeah, that's an important skill, but moving forward, I really care that you understand why things are used and why things, like, we use acids for a reason. We use acids to make electrophiles better. We use bases to make nucleophiles better. An acid has to be taken by something with electrons. So I'm going to look for the thing with electrons to take the acid, to take the proton. Cool?
Yes.
Okay. We're going to kind of approach this from a different angle tomorrow. I'm kind of excited about it. So far, we've just been doing one reaction, but tomorrow we're going to start talking about stringing multiple reactions together to make a desired product, which is a different skill set. So tomorrow's an exciting day.
Will that be on the exam?
Yes. Anything up until Fridays, or anything through Wednesdays, fair game for the exam.
Okay.
Just like a quiz. I'm not going to be adding any new reactions necessarily, but just how we use them will be different, if that makes sense. To give a sneak peek, if Arlo's gonna be, let's see. Oh. Headphones going. So yeah, he keeps taking my headphones. This isn't good television. But essentially, like, an example question would be like, if I said start with this and I want you to eventually make, this. Well, you would have to know that in order to get this, I need to do a substitution. In order to get a substitution, I need to install an alkyl halide, right? So it would be, right, I do a addition reaction to get this, and then I do a substitution reaction to do this. So can we string together a couple of reactions to get a desired product is what we're going to do next. This is called synthesis. This is kind of the next step. This is, right, if you're a chemist, you'll be like, this is the drug molecule we want to make, but this is the starting material we have. So what reactions do we need to do to go from point A to point B, right? And sometimes it takes multiple steps. So that's what we'll be doing tomorrow. And that will be on the test, but we'll hopefully get plenty of practice doing stuff like that. And I think it will also help you guys see the reactions from a different perspective. All right. Well, I'm going to go. Thank you guys for coming. Any other quick questions before I head out?
I had one question,
What's
and it
up,
was
Joe?
this: what is the specific definition of SN1?
So it's a nucleophilic substitution that is unimolecular is what it means. It just means that, so the slowest step is what's called the rate determining step. And the slowest step of an SN1 is the leaving group leaving on its own. and that just involves one molecule, right? That's just one molecule who has its leaving group leave, right?
Okay.
Whereas with an SN2, you have two molecules interacting, right? You have an attack at the same time as the leaving group is leaving.
Mhm.
So that's why it's called SN2, because it has to do with two molecules interacting. SN1, the leaving group leaves on its own without being pushed off. So that's why it's called SN1. Hey, dude.
Okay. Thank you.
It's kind of backwards to how it's easy to teach. It's easy to teach it and say, hey, this is a 2-step and a 1-step.
Mhm.
But if I say that, it makes it confusing because an SN2 is 1-step and an SN1 is 2-step. But it has to do with molecules interacting in the rate determining step, which is kind of confusing. So whatever helps you guys remember it is what matters to me.
Okay.
So if you have to remember, when I was an undergrad, I just remembered that it was opposite of what I thought it was.
Yeah.
And that helped me. Because I'm not going to ask you for the definition of unimolecular rate determining step in this class, but yeah, that's why it's called that. And I did not come up with the names.
All right. Thank you.
Yep.
Thanks, Kevin.
Yep.
Thank you.
See you guys. I'll see you
Have a
tomorrow.
good one.
See ya.
Bye.